Welcome to my video on thermochemistry. Thermochemistry is the next topic we're going to get into, and generally if you look at the breakdown of the name thermochemistry, it makes some sense. Thermo, we're going to talk about heat and heat transfer, and of course we're going to talk about this in relation to chemical reactions and so forth. Let me straighten out that line a little bit. So what ends up happening is we're going to start putting a little bit of heat into these equations and talk about heat going into and out of reactions. And more generally, we could talk about energy as well. And basically, the production of energy is one of the most important aspects of chemistry. The digestion of foods powers us as human beings, and that energy originally came from the sun. So you had photosynthesis that was storing energy. As we eat and digest food, we release that energy to run our bodies. When you drive cars, when you heat your home, you're burning fuels. Electricity for your home. If it's not a nuclear reactor, probably somebody somewhere is burning something to drive a turbine. So energy is a very, very important aspect of chemistry, and that's what we want to get into a little bit. Basically, thermochemistry is the study of the relationship between reactions and energy changes that occur. Now, in terms of energy, there are two broad classes of energy that we can talk about. One of those would be kinetic energy, which is the energy of movement or motion, and the other is potential energy, which is basically stored energy. It's the energy of position. So, throwing a baseball, of course, it has kinetic energy as it's moving along. Potential energy would be if I'm holding the baseball up high, it's not stable, and if I release it, of course, it will fall, and that potential energy will turn into kinetic as it moves down and so forth. Now, chemical energy is oftentimes looked at as a form of potential energy, because what's happening is chemical energy is the energy that can be released or absorbed based on the arrangement of the atoms. So if the atoms are in a very unstable arrangement, there's a lot of potential there for the rearrangement and the energy that would come out as that is released. It is typically measured in joules, and the reason I have that is this gentleman over here you see on the right is named James Joule, Joule, and the unit that we use to measure energy is joules. It is Joules, and so we're going to measure energy in what we call joules. The abbreviation is a J, and that's how I do my J's. It's obviously named in his honor. He is also somebody who developed what's known as the first law of thermodynamics. Very simple concept, really, but he was able to test it and prove it. And what he basically said is if you have a reaction releasing energy, the energy transferred through that reaction, if it's released from the reaction, the amount of energy released from the reaction is the amount of energy absorbed by the surroundings, and vice versa. If the surroundings are releasing energy, the amount of energy released by the surroundings will be that absorbed by my reaction or what have you. So, makes some sense. It's kind of the law of conservation of energy. It just says, if one thing is releasing energy, the surroundings will be absorbing it, and vice versa. Now, a couple of things with that. What I want you to understand what heat is. Heat is a very, very important concept, and a lot of times people kind of confuse heat and temperature. Basically, temperature is a measure of the average kinetic energy of particles. So what will happen is if you're looking at some sort of an object, it's made of particles. So let's say we have a gas and you have these particles. These particles are moving. The faster they move, the higher the temperature and the higher the kinetic energy. So the faster they're moving, the hotter this is, the higher the temperature. Let's say I have another object, and this has the same particles or same number of particles or a different number, it really doesn't matter, but they're moving a lot slower. These guys are not moving nearly so fast, so they have less kinetic energy and a lower temperature. Well, now what would happen is if we measure the temperature, measure the average kinetic energy, let's just pick a number. Let's say this is 20 degrees C. Let's say this is a higher number. Let's say these are 30 degrees C. If I bring these objects in contact with this object, these faster moving particles will hit these slower moving particles, causing them to speed up. So they'll go faster, and this energy that's being transferred is what we call heat. So this is what heat is. Heat is this transfer of energy. It will always flow from the hotter to the cooler thing. We will look at this through a couple of variables. One of the most common is Q that I'll be using, but heat again is not the temperature. The temperature is a measure of the movement of the particles, but it's the transfer of energy that occurs as you go from the hotter to the colder object. So it will always flow in that direction. Now, this whole idea of Q, there's a couple of variables that I'll use. Q is heat. If I had some, say, water, and I wanted to know how much heat was being absorbed by the water, I can actually use a formula that the heat absorbed or released by something is equal to its mass times its change in temperature. That's a triangle. It's a Greek letter delta. It's delta T, means change in temperature, times the specific heat, which is abbreviated by C. Some people do C sub P. And this is simply the amount of joules per gram degree C. I'm sorry, I didn't mean to put that one there, but joules per gram degree C. That dot should be down here. So basically it's saying for every gram that I take up 1 degree C, how many joules are required. As an example, water is 4.184 joules per gram degree C. So what happens is if I want to take 1 gram of water and raise its temperature by 1 degree C, I have to put in 4.184 joules. So really what we're doing here is we're taking the specific heat times the number of grams times the number of degrees temperature change, and that tells me how much heat in joules would be required to do this transition. Now again, going back to this first law of thermodynamics, I could write this like this. I could say the Q of my reaction is equal to the negative Q of the surroundings. And so what would happen is if I was doing some sort of an experiment and I wanted to measure how much heat was gained or lost, I would simply take the mass of my thing that I'm taking the temperature of. Oftentimes it'd be water if you're doing an experiment in water. And you can take the mass of the water times the temperature change in the water times the specific heat of the water. In this case it would be 4.184. And then I can figure out how much heat was released by the reaction by seeing how much was gained by the water. So it's just kind of a simple look at it. Now, one other thing that you should be aware of is that when I talk about reactions going through and releasing energy and so forth, the energy is equal to both the heat and the work that's done. Well, in these reactions, I'm not so much worried about work as I am about the heat only. And so in chemistry, we're going to use capital letter H, which actually refers to just that energy transfer, that heat transfer, and that is going to be the enthalpy of a reaction. Now, enthalpy is H. It is difficult to measure the exact enthalpy of reactants and products in a reaction, but what I can do is, again, use this delta again. I can fairly easily measure the change in enthalpy or the change in heat by doing these sorts of calculations. The delta H, or the enthalpy change, is going to be the enthalpy of my products minus the enthalpy of my reactants. So if we were to look at, say, an energy diagram, you can have a couple different variations on this, but one option would be something like this. If this is my enthalpy here and this is my reaction, if I have my reactants here, my products here, what will happen is I put a little energy in. It's called the activation energy. I'll talk more about that later. And if my products are lower in enthalpy than my reactants, this difference is the energy that would be released by the reaction, and of course that is my delta H, or the change in the energy. It's also my Q. So notice my products are lower in energy than my reactants, so if I take the H of the products minus the H of the reactants, this is a lower number, this is a higher number, so my delta H would be a negative number. So negative means this reaction going forward is going to release energy, and it will be exothermic. It's going to release energy. Now I could also have a situation, and let me put this down here, where here are my reactants, here are my products. My products have more energy than my reactants. So I would again have this activation energy, and it could look like this. And so notice now if I take the H of my products minus reactants, the products are higher than my reactants. So this is a higher number minus a smaller number. So my delta H here is going to be positive. And since energy is going into this reaction, this will be an endothermic reaction. So that's a little bit about enthalpy, thermochemistry, and joules, and how we're going to do this sort of work in measuring these things. I need to discuss this in a little more detail later, but we'll do that in the next video.